let's move on and have Johannes get his slides ready. Johannes Kaiser is going to talk with us about the GFAS system, and I'll let you introduce yourself, Johannes. Thank you very much.
Okay.
And I'll
yes.
promise not to cut you off early.
Okay. Thanks, Nancy, and thank you everyone for coming and listening in. So I'm Johannes Kaiser. I work since last week at Nilo in Oslo, and I've been working on GFAS, started working on GFAS when I developed the first version at ECMWF. The whole thing is set up in CAMS, therefore you get this nice layout. The other people who have been really participating and contributing to these are Mark Parrington and Ansadi Tomaso, who is taking over at ECMWF as project officer for GFAS, and Martin Wooster with a large team of postdocs over the years who've done very fundamental parts of GFAS. I said it's, how do I get the next slide? It's just slow. So this is part of the Copernicus Atmosphere Monitoring Service. You may be aware Copernicus is a European program for Earth observation, funding satellites, but also 6 thematic information service providers. And so this is within the Atmosphere Monitoring Service. The users of the products are free, and access is unrestricted for this. So it's a big public effort here, consorted public effort. The idea of this Copernicus Atmosphere Monitoring Service is to use Earth observation data, mostly from satellites, but also in situ, in order to run forecasting and monitoring systems globally at ECMWF and in an ensemble of European air quality forecasts, where the global system produces twice daily 5-day forecasts, and the European air quality is produced daily with 4 days ahead. The system has a big outreach with more than 20,000 users, 3,000 ahead of them, a lot of visibility in the media, and users like Windy are a big multiplication factor in the non-scientific community there. The good thing is that it also has routine validation, and the fire emissions go as lower boundary into these atmospheric systems. So that's why we're using it, why we're doing GFAS. So this is the main use, but of course it's been used in other atmospheric chemistry models, and it's used for communication activities and climate monitoring in the climate in the BAM state of the climate reports and C3S state of the climate reports. GFAS, here is a link to a documentation, is based on failure radiative power, currently based on MODIS instruments, but soon also on VIRS and Sentinel-3. Currently, there is a daily output which is 1 day behind near real time, and there's a version with hourly output. It gets updated every hour, and this is 7 hours behind real time. The emission factors are estimated with vegetation type dependent, emissions with vegetation type dependent emission factors as usual. And there is an additional product on injection heights, which is calculated with a plume rise model, and another one based on the IS4 FIRES parameterization. So I'll focus on the emissions and give you an overview of how we are calculating the emissions based on the satellite FRP. So the first step is really gridding the satellite level 2 observations to get a representation that is easily comparable and treatable. And this gridding includes the non-fire observations. So we say there is a fire, but also we say there is observation of there is no fire. And based on then satellite products from several satellites are merged into a continuous representation of the FRP field in time and space. And I'll go through all the arrows on the right-hand side during this presentation, so I'll mention them in time. The continuous FRP field has components from gas flaring and other spurious signals, so it gets masked to obtain a vegetation FRP field, and then this is converted to the dry matter combustion rate using a conversion factor, and the combustion rate is then converted to species emission rates, or when you integrate species emission budgets. And Guido already mentioned the aerosol enhancement, so we recommend the users to use an enhancement on the aerosol emissions, but not on the gases emission factors. The whole step from vegetation FRP map to the emissions, gases, and aerosols can also be done in one go. And an important insight is that that these arrows that are in red are really empirical factors that need to be calibrated in order for the system to work. So that's different from the approach of GFAT, where we really say we need some calibration in the system for GFAS here. So let's go on. The observation precision. When we have our fire observations, every fire pixel has got signal to noise associated with the radiance. So this signal to noise ratio is propagated through the FRP retrieval algorithm in order to derive an estimate variance, standard deviation variance of the FRP detection. And you see on the right-hand side here distributions of these standard deviations for VIAs on the left and the two MODIS instruments on the right, and they are obviously a bit more uncertain. And then when you do the comparison between MODIS and a geostationary satellite, VIAs, Severi here, you see that, again, the geostationary is more uncertain. For the non-fire pixels, we use the detection threshold as an approximation for the standard deviation, the accuracy of the observations. And here the red line gives an approximation of the detection threshold of MODIS, how it varies with the view zenith angle on the x-axis. And all the dots are individual observations. When we plot now an observation for 1 hour, you can see the satellite tracks on the top plots are MODIS tracks, and in color coded is the inverse variance that we estimate based on the detection threshold. And you see in the subsatellite point it's more accurate, and then towards the edges of the swath it's becoming less accurate. You also see where there are no observations due to cloud cover. In the bottom line is on the right is VIAs, and you see the higher accuracy in the subsatellite track. And to the left is an example for Severi, and you see that generally it's got with the higher detection threshold, it's estimated to be less accurate, and all of them have basically the same clouds that are appearing. So we know the FRP, gridded FRP, together with its uncertainty. If we want to combine them, they also have to look at biases for the FRP. So the biggest difference, it's clearest when you compare low Earth orbit and geostationary satellites. So here on the left is FRP from Severi over FRP from MODIS for observed fire clusters. And what you see here is that when both observe fires, they really agree very well in their FRP retrieval. So it's basically a one-to-one relationship, unbiased. However, when we grid the observations, and for example, to a 2x2 degree grid, then we get the relationship on the top right, where the Severi FRP is underestimated by 57% when compared to the MODIS FRP when you look at, for example, a monthly average FRP per this grid cell. And this really comes from the large satellite pixels of the geostationary observations, where you have many time slots where small fires are being missed with the higher detection threshold. But that's not the whole story. In the top here, you can see the grid cells where Severi saw more fires than MODIS in a 1 year time period. And on the bottom, you see a map of the grid cells where MODIS saw more fires than Severi, so the other way around. And you can see that it's really intertwined, and neighboring grid cells may have an opposite bias. And this is really due to the fact that in addition to the higher detection threshold, which makes Severi misfires, it has the higher frequency of observation, so that shorter fires, which happen only between the MODIS overpasses, they can be seen by Severi, but MODIS misses them completely. And this is the disadvantage of fire radiative power compared to the burnt area observation, that you cannot see the fire once it's stopped. You cannot detect it anymore. However, what we did was we derived bias correction factors, and we did that such that the assimilated FRP budget from this from using only one satellite in GFAS should be the same for whatever satellite we use. So should be the same as when we use both MODIS instruments. That was our baseline. And we did this separately for daytime and nighttime. And you see in this list here for the low Earth orbit satellites, there are big differences between daytime and nighttime because they sample the diurnal cycle at different points in time. Whereas for the geostationary satellites, the difference is not so big because they sample the entire diurnal cycle. And when we do this, we ran the GFAS assimilation with various combinations of different satellites. And on the right here, you see different satellites, different combinations of MODIS, VIRS, and Severi FRP observations for 3 days, and then the integrated fire radiative energy over the Severi disk. And you see that with these correction factors on a large region, on a continental scale, they work pretty well. However, when you look into, no, one step ahead. That is what is in the current system. There is a separate development we did, which is not in GFAS yet. This was looking at just MODIS and at the different biases which you get across track for the different viewing angles, where the larger viewing angles are have a larger footprint size, and then you get the probability density functions here for the different bins of viewing angles. And you see the further you're off track, the fewer of the small fires you get. You can't see small fires at all, and you get smaller fires at each size. But this is gridded, 1 degree gridded. So you know in each grid cell, the order in which these grid cells are ordered by fire size should be the same. And so what we were asking, how do we need to elevate the FRP in these grid cells such that they reproduce the most accurate observations, which are the ones up to 6 degrees nadir? So how do we get from the left to the right probability density? And obviously, there are small fires being missed here when you do that, but the larger fires, you get a correct representation. And we found that there was a very systematic behavior, which really depends based on the FRP in this grid cell in a small area and the viewing angle, and then which we were able to parameterize. So that is something where we can get better in the future than just applying two different factors for each satellite, and where the bias correction, we should be able to do it for different situations more accurately. But it's not implemented yet. So fire model. In GFAS 1.2, we had daily average persistence and an inflation of the variance of FRP. In GFAS 1.4, we have daytime and nighttime persistence separately. So we keep track of the daytime, local daytime level of FRP and the local nighttime level of FRP, and we inflate their variances separately. And then in order to obtain an hourly resolution, we superimpose a diurnal cycle with a fixed Gaussian, with fixed peak time and fixed width. And we just adjust the amplitude of the Gaussian so that the mean daytime level is being reproduced. So it's not really 1 hour time resolution, it's more like 12-hour time resolution. And then the developments we do to improve that in the future have been done in a Code for Earth project where 4 PhD students looked at fire forecasting, and their task was to look at the GFAS FRP in a certain grid cell in a 24-hour period and then forecast the FRP for the next following 24 hours and do the forecast based on the last 24 hours of FRP and the meteorology for the entire 48-hour period. So where this comes from numerical weather prediction. And they trained a neural network besides other models and were able to improve the mean average error compared to persistence, just repeating the diurnal cycle from the day before, and improve the root mean square error as well, and also improve the correlation. So the correlation improves from 0.64 to 0.82. So it's a quite big improve even with a relatively short project which they could achieve. And what this looks like is shown here. Again, you have in black the GFAS, where on the right-hand side now the black curve is the reference. You have in red the forecast, and you have in the dotted lines the different meteorological parameters. The green is the soil moisture, and you see that here's an event where it jumps up, so it's raining. At the same time, the temperature is dropping and so you really see here is a rain event which extinguishes the fire. And simply based on this information, they were able to extinguish the fire in their forecast and even produced a smoother, more realistic diurnal cycle than GFAS with all the artifacts from the superimposed diurnal cycle. So that's very promising for the future. And when we put all this together, we bias correct the observations, we use the precision and the fire model, then we can do a data assimilation approach. So in the top row, you see FRP fields over Portugal and Spain. In the bottom row, the associated inverse variance, so precision estimate. To the right is the background, so that's the persisted forecast from the previous time step together with a low inverse variance, inflated. And on the left, you see a modus observation, then a severe observation, and then these three columns are merged together. You get to do a weighted average where the weights are given by the inverse variance in order to retrieve the best estimate of the current FRP field. So that's at the core of GFAS, how it's able to fill observation gaps, because where there are clouds, you don't get anything from the observations, but you get it from the background then. And you see that in these cloudy regions here, it says we have information, but it's low quality. Does it work? This is from a paper that showed observations of fires during the El Nino in Borneo in 2005. You see here this smoke plume, and the red dots are MODIS fire detections. And then there was a manual analysis of observations by TED1, and you see the fire detections in yellow in this stripe of TED1 observations. And so it's obvious that there are fires under the smoke which are just not being detected by MODIS. And when you compare to the corresponding GFAS map, you see that the fires there are fires represented under the smoke. So they have been ignited and observed before the smoke got too thick. And then GFAS persists them until it gets an observation that says there are no fires anymore, and then they get extinguished. So it works well on a large scale. This is an example on a small scale, again, Portugal, where it doesn't work so well. On the top row, you have for 5 days of observations of MODIS in blue triangles and Severi in gray colors. On the right side, you see there is partial cloud cover. So sometimes you see the fire, sometimes you don't. And in the bottom is what different configurations of GFAS make of this. So the red is when you just do daily averages. The blue is just using MODIS, and you see that there are really from this diurnal cycle, there are artifacts in the estimate, and then they get reduced when we add in the Severi as well. But at the same time, we get new features from all the Severi observations. So it's struggling a bit on the smaller scales. That's a lot of the effort went into producing these continuous FRP fields. So once we've got the continuous fields, we need to get rid of spurious signals. This is the map that's in the operations at the moment, where you see Galapagos at Iceland, where ad hoc masked out when there were volcanic eruptions. It's a coarser resolution, and this is the new map that has been derived at a much higher resolution, which includes a static volcano map, a persistence analysis, and on MODIS and VIAS, and then the attribution of in the MODIS and VIAS ML products of volcanoes and land and offshore spurious signals. After the conversion, after that, we need to convert FRP to combustion rate. And I said earlier, this is an empirical factor. And so we need some reference. And the operational version still has GFAS3 as reference. And Martin Wooster had shown in the lab that there is a universal factor for this conversion, which is independent of fuel type. But we have seen that it actually, when you look at satellite observations, it depends. For example, for the peat, you need a much larger factor, because it's simply the thermal signal is trapped in the ground instead of being visible to the satellite, whereas agriculture is very well seen by the satellites. But really, we have a challenge at our hand to identify an appropriate land cover map which isolates the different proportionality factors, and then to update these empirical factors. Then calculating emissions. This is, Mark has shown this already from Christine's paper on FIN. So there are big differences. One thing that strikes me is how ammonia in GFAS in equatorial Asia is so different from all the others. And I think it's due to the emission factor of peat that well, it is obviously due to the emission factor of peat fires that we're using. So we need to update that. We had, so far, we had the old emission factors from Andrea and Merle, and we have just updated the emission factors in our development version to Andrea 2019. Aerosol enhancement, Guido mentioned this already. This is the image from the publication that he referred to, where we used the average, temporal average over several months of aerosol AOD from the analysis, which is constrained by MODIS AOD observations as a reference. Then we had a model run, saw the AOD is much lower. And then we just looked by how much do we have to elevate the AOD to obtain the same aerosol load of AOD as in the analysis. And we found this factor 3.4, which had been used in CAMS, but we also saw after the model has been developed further, in particular after secondary aerosol formation has been implemented in the aerosol model, which is used for the CAMS global forecasts, we had to lower the factor by down to 1.5. So this is really, we see that it's something, it's got to do with atmospheric chemistry, how well is smoke plume chemistry represented, so that's something that's not only depends on the emission inventory, but also on the atmospheric model which you use the emissions in. Guido has already mentioned the inversions, and I've got a few slides on that as well. So basically what we did with aerosol was sort of an inversion, and we tried to, this is ongoing work here, it's not really, you see wherever it says CAMS, it's an internal project report. We really try to generalize this a bit and fit, for example, the regional time series of AOD and carbon monoxide over Australia. So it's integrating the AOD over Australia and then creating a 1-year time series and doing this and having and tracing which fire type the AOD comes from. And then by fitting the time series to the analysis again, so as a representation of the satellite observations of AOD, we can redistribute where the smoke comes from, and we see that it's much more extratropical forest and much less savanna than was originally estimated in GFAS. And when we do this for different continents, and then the image changes. This is AOD, the analysis. In the middle is what the normal model that's in the forecast would do, and you see in Australia it's overestimating here this savanna proportion, and after this inversion type adjustments, then you see this has been lowered, and the plume here has increased a little bit. But you also see the difficulty when doing this. In reality, the plume is much wider than what the model represents. So you really struggle to identify the right features. Thanks a lot, Guido, for your introduction on the inversion. This is really my thought of what we should, how we should go on. And that's do an inversion of a species which has a very good observational constraint and where we have good knowledge of an emission factor. And I've also thought of carbon monoxide. And then we could either do go for an emission flux inversion directly and then match that to a GFAS, or we could go for a parameter estimation of this coefficient of emissions. And then afterwards, after we've done that, after we've constrained the carbon monoxide, just as you say, calculate the conversion factor, which in our case then would give the dry matter, not the carbon, but the dry matter, and then use emission factors for all the other species from the literature, and maybe adjust some of them later with dedicated inversions. But on top of that, I think we will also, when every user will need to invert the AOD and determine their own aerosol enhancement factor. So I've shown you on the last plot an approach which we followed to do this offline in a very cheap way. You can also look at the paper by Joe McNaughton, who has implemented flux inversion in the CAMS model, in the global CAMS model. And we are planning to use that for the inversions as well. So that should be online and with all bells and whistles. To summarize, GFAS has really an emphasis on the assimilation of satellite FRP. So it's trying to fill the observation gaps due to clouds and the satellite orbits and the detection thresholds. We have several new developments in the pipeline which are maturing towards operational deployment. In particular, the fire model based on machine learning combined with the bias correction based on the probability density function matching, that should allow us to merge observations from low Earth orbit and geostationary satellites with a true 1 hour resolution. But then we'll always depend on a calibration with top-down or inversion approaches. And one thing which is very nice, our main user is the CAMS model, so we can use all the constraints and the analysis and the inversion approaches of the CAMS model in order to derive emissions that are really optimal for our main user, and at the same time yield new information for the wider community. And the other topic that Guido showed is how it's the dependence of all these factors on fire type or modified combustion efficiency, fuel, moisture, land cover. So we don't have this included, and we should in the future. So I hope we can learn from you there, Guido. And I want to finish just with an overview of the different versions of GFAS. So we've got the 2 operational versions with numbers. We've got one version, development version, which is running on the supercomputer at ECMWF, and we've got one version that can run on a PC. And we sort of migrate the developments from the right-hand side to the left-hand side more and more. So we have in the PC, on the supercomputer, we can use VIRS, NPP. On the PC version, we can also use SLSTR, GOES, and Himawari. I forgot to mention Severi there, which is so we should add this in your mind together with the bias correction, all of these. And then we have the new emission factors on the HPC version, the new land cover, new Spuri signal mask so far on the PC version, and the developments on the fire forecasting and the FRP dependent bias correction. They are currently completely offline, not implemented yet. So thanks for your attention.
Thank you very much, Johannes. That was excellent. I learned quite a bit. I appreciate. I told someone this workshop is kind of like, I want to read the book, but I don't want to spend time reading. So I get to learn it all through all you experts. We have one question from Shobha that we can look at. Johannes, view angle dependent FRP bias correction may not be needed for VIRS as its pixel only grows minimally with the scan angle compared to MODIS. Did you look into VIRS for this? That was my question too. Where are you in your exploration of transitioning away from MODIS? And this question that Shobha brings up, or concern or non-concern.
The comfortable thing is that we don't have the view angle dependent bias correction in the operational system yet, so we can put in VIRS, and we have these. Let me show you one thing. We looked at VIRS. I've got a backup slide on VIRS somewhere here, and I need to share this again, right? So this is the image with the detection threshold, which we showed for MODIS, and this is the one for VIRS. So really we see that only at the very edge of the swath the detection threshold rises. That's correct. But we see that we need different emission factors, correction factors. So when you look at this table with the, let me just check, where is my bias correction table here? This one. We see that here, when you look at MODIS, Aqua, and VIRS, really during daytime, they see virtually the same amount of FRP. So we put in this bias correction factor, and then we can use VIRS NPP. What we are currently don't understand is why we see much less fire during nighttime with vias. But in principle, we have a system running on HPC where we can switch vias on, and it will produce FRP that's consistent what we do with Modis. Does that answer the question?
It's good to see that you're looking into how VIIRS is going to be able to be taking over the problem set we have, which we know is going to be the way to go into the future. We have a question from Johannes Fleming. Diurnal cycle of the biomass burning emissions is important for vertical mixing and transport patterns. Could you explain in more detail how diurnal cycle is derived for the current GFAS and plans for the future?
Okay. Let me go. It's basically this this slide, but I'll show you another one on that. Let me just check. I can, this slide. So what happens when you look to the top right plot here? GFAS, the state variable in each grid cell is the daytime FRP and the nighttime FRP. So here, when you look at the red dotted line, that's the daytime FRP, and this is the estimate, the persistence estimate from the last day. And when we get a MODIS observation, blue here, which is below, then this is adjusted down according to the observation. And when we get a MODIS observation, which is above, then the daytime FRP is adjusted according to that. And of course, it's not completely there, but it's this weighted average between previous observations through persistence and the new observation. So at every point in time, we have one estimate for the daytime FRP, and the same happens for the nighttime FRP. And then based on these two values and the local time, an FRP is calculated from this parameterization of the diurnal cycle. So there is a background level due to the nighttime, and then there's a Gaussian curve on top of this background. And it's the amplitude of this Gaussian curve is adjusted such that the curve, the integral under the curve from morning to evening equals the integral under the current daytime average FRP. So that's what's currently being done. So it's really a superimposition, and you get this, and to the right, that's a quite typical shape that you get from this approximation. And it cannot handle a fire that's earlier or later. It just assumes averages. And that's why you get different bias correction factors for MODIS observations in the morning. They get corrected up, and observation in the afternoon, they get corrected down towards this average daytime level. What we want to do in the future, I think the best what we should is to follow this machine learning approach in order to predict this the FRP at the next time step based on the last 24 time steps and the metrology changes in metrology.
Thank you, Johannes Fleming. Hopefully that answers your question. And at this point, if we don't have any other questions in the chat, unless anyone wants to add to the conversation. Well, we can end a little bit early. We're pretty close. I would like to make a few comments. Johannes, that was excellent. Again, I really appreciate you spending the time to go into the deep details of how you're approaching all of the aspects that are kind of black boxy to me sometimes.
They are, yeah.
And I appreciate your last bullet on your last slide related to, again, fuels and variability of what's happening on the ground, because that's, I think, where the action is, which is good for me and those of us who love being in the field. So
yeah, no, I think we really need you there at this point.
well, not just me, but yeah, my compadres, exactly. We will be moving into a break right now because it's a lot to absorb. We wanted to remind you that we have a pre-workshop survey. There's a link in the chat that you can find. You can find the agenda there. We have 3 more presentations today, and Cindy will be taking over as moderator. And really appreciate so far what we've learned. Be sure to do that survey and also fill out the Slido question on where you're coming from. And we will see you in, I guess it's 10, 20 minutes.